Hello and welcome to Good Drugs. I'm Michael Fiedler, PhD, and I'm of the belief that in order to get through this thing called life, we need potions, elixirs, magic pills, and it's just a matter of finding good ones. But today, I want to focus on something a little bit different. I want to focus on a dead drug. And the reason why I want to focus on a dead drug is that these swings and misses by pharma are really as influential as well as the home runs in terms of our research and discovery about human medicine. And unfortunately, these high profile failings, if you want to call it that, are sort of they show up in the financial news at the time because stock prices drop and people talk about money being lost. But the science and the energy and the momentum for them is essentially falls off a cliff, and that's unfortunate because we learn a lot about medicine through these failings. And I thought it was worth touching on a drug that didn't affect necessarily me, but did affect, but it did it's directly, but it did have an effect on me indirectly. So the drug that I want to talk about is Torcetrapib. It was marketed or attempted to be developed by Pfizer, um, and it worked by increasing HDL or high density lipoprotein. And so, what I want you to do now in your mind is go back to the early 2000s. And I want you to think about where we were in terms of public health. And the big issue at the time was obesity. A lot of people were getting type 2 diabetes, and not to say that there wasn't happening before that, but that was sort of when obesity was very top of mind, the way things like mental health are today. And there was a lot of innovation to go into an attempt to do something about increasing levels of obesity, and more specifically in terms of medicine, a condition called atherosclerosis, which is when you have deposits of cholesterol that clog your arteries. And that can lead to a number of things. It can lead to a heart attack. If one of these clots shows up in a blood vessel that feeds your heart, it can show up as a stroke. If it blocks blood vessels in the brain, it can show up in your legs, and it can also show up in your lungs. And that one's called an embolism. There was a lot of attention to this, and there were a number of drugs available to treat cholesterol that were approved. That you may be familiar with drugs like Lipitor, and these fall under the class of statins. And statins, there's a number of them. There's a atorvastatin, simvastatin, and they were sort of standard of care for the treatment of high cholesterol. Your grandparents may have been on it at some point or another, but pharma tried to level up in terms of their ability to affect atherosclerosis, which is sort of an endemic problem in obesity, and it kind of is sort of gets tangled up with type 2 diabetes and a number of other things, diabetic retinopathy, which is an eye condition. But unfortunately, it didn't work out despite best efforts, and torcetrapib was a very high-profile failure. So I've sort of given a very sweeping introduction, but let's start with more about what cholesterol is, because that's what we're going to be talking a lot about. And cholesterol is a very complicated carbon molecule. They're pretty good size. They're very sophisticated. There's lots of different types of cholesterol, but they're made in the liver, and it functions to create a number of things in the body, or to facilitate things in the body. One of the first and foremost is a membrane. And membrane, the best analogy I can think of is, imagine like a fitted sheet on your bed. You want that fitted sheet to fit just perfectly over your mattress. And you can have a queen size, twin, California king, and cholesterol sort of provides that elasticity. It gives cells the ability to kind of have just the right viscosity to sort of function in a homeostatic fashion. And too much or too little cholesterol can be a bad thing, much like if a fitted sheet is sort of too big or too scrunchy or too whatever. So that's sort of what cholesterol's function is in terms of membranes. They're also used in hormones. So hormones, you think of things like estrogen or testosterone. Those are all cholesterol based. There's one hormone called aldosterone that's going to come up later that affects things like blood pressure. And hormones are molecules that function similar to neurotransmitters in the sense that they transmit signals in the body, but it's more about like your nuts and bolts body function, like how your digestion works, how your kidneys work, how your heart works, rather than like your neuro firing and how your mind works. And then one of the last functions that I want to talk about a little bit is bile, and which is used in digestion. It helps solubilize materials in your stomach because you're going to eat a whole host of different things, and we got to get all of it in solution. And bile is a tool that your body uses to help solubilize or put into an aqueous solution stuff that you eat, and cholesterol is a big important part of that. So cholesterol has functions that are important in your body, although it kind of gets a bad rap because we think about it with sort of obesity and sort of like poor cardiovascular health. And the reason why that is that it's a disproportionate relationship of types of cholesterol. So low density lipoprotein, or LDL, is what's known as bad cholesterol. And this bad cholesterol collects on the insides of arteries, and that's how you get atherosclerosis. And that's what statins like Lipitor do to reduce. And they inhibit enzymes that make LDL, and so you get a natural decrease in it. It doesn't actually lead to like necessarily like improved fitness. It just sort of prevents your body from chemically being able to make low density lipoprotein. So it has its value, its standard of care for the treatment of high levels of cholesterol, which I said bubble up to a number of other different conditions. And that's the bad cholesterol. You want low levels of low density lipoprotein. It's sort of the spackle that gets stuck on the inside of your arteries. But then there's another cholesterol molecule called HDL, or high density lipoprotein. And this molecule functions very differently. It functions kind of like a garbage man that is sort of floating through your bloodstream and scooping up particles of LDL as well as others. But it is thought to retrieve cholesterol from the bloodstream and return it to the liver, where it can be processed into other things. So there's this feedback loop of sort of LDL, sort of cholesterol going out into the body and being used for various functions. But if you got too much of it, it collects in your arteries. And then there's HDL, which sort of retrieves it and brings it back to liver so it can be processed. So for a long time, it's been known that low levels of HDL and high levels of LDL invariably lead to poor outcomes. And so the first sort of wave of cardiovascular drugs were these statins to lower your LDL. And then there was this thought, well, why can't we just increase levels of HDL and maybe it will have an even better effect on cardiovascular health? And a number of drugs were investigated to test this hypothesis. Torcetrapib being one of the early ones. There was a number that follow, which I'll get into in a little bit later. And the way that this drug works is it is a CETP inhibitor, which is a cholesterol ester transfer protein, CETP inhibitor. And what CETP is it essentially unloads HDL. So when HDL gets sort of like filled up and bulked up after picking up all of the LDL particles, it goes back to liver, and CETP removes that those cholesterol molecules and transfers them to other cholesterol intermediates. It's sort of where it offloads its cargo. And there was a lot of preclinical evidence that said that, if you knock out CETP in a mouse model, which means you eliminate that functionality, you can kind of get, or at least reduce the levels, you kind of get positive cardiovascular outcomes, or at least one would think so in terms of cholesterol levels. And high HDL was associated with, and it increases levels of circulating HDL, which were associated with good outcomes. So there was sort of emerging evidence that if we could target CETP, we could increase levels of HDL. And the assumption was if we increase levels of HDL, we'll have positive effects on cardiovascular health in these atherosclerotic situations. And so a number of drugs were attempted to go down this CETP inhibitor pathway. Torcetrapib was, as I said, one of the early ones, but there were a number of others. There was a drug called anacetrapib that Merck was championing. There was a drug called evacetrapib, which was from Eli Lilly, and then dalcetrapib, which is from Roche Genentech, which was the first drug I was intended to work on when I first got started in medical communications. And so some of the first work I did was in cardiovascular disease. And torcetrapib had a pretty cataclysmic failing in the sense that the drug actually killed people. And that happened in the middle 2000s. I think the New England Journal of Medicine paper that was highlighting it was published in 2007. And that was sort of the first failing of this therapeutic approach, which was you had patients with, it didn't necessarily, it was thought to be an off-target effect at the time, and actually still is considered to be that way. It wasn't that torcetrapib was increasing HDL to the point where it killed the patient. What happened was it had the off-target effect of increasing levels of aldosterone. And as I mentioned, aldosterone is a hormone that controls blood pressure. And so you had spikes in blood pressure from various patients, and they died both of cardiovascular and non-cardiovascular complications. I should also say that torcetrapib really cranked up HDL levels, and that will kind of come up later. But that's possible that you just cranked up the system too hot, and you made too much aldosterone, and these people died. So following that, a lot of these other companies that had invested a lot of money and had high expectations for the use of these drugs really focused on the safety of the drug. I'm like, okay, are we getting this blood pressure signal? You know, our drug is safe. No one sort of seems to have this issue. Um, and some of these drugs were less potent on HDL formation. Dalcetrapib being one of them. Anacetrapib and evacetrapib were almost doubled your levels of HDL, whereas dalcetrapib was only increasing it by about 30%. So there was a lot of voodoo and hocus pocus on the safety of increasing HDLs in these CETP inhibitors. But what really was the nail in the coffin was that the drugs just simply didn't work. In the phase 3 trials for dalcetrapib, there wasn't a improvement in cardiovascular outcomes. It just didn't do anything statistically significant. And I should say that that doesn't mean that the drug did nothing. It just did nothing on top of standard of care. And when you're investigating drugs for which there already is a drug, a condition for which there already is a drug, like atherosclerosis, which already has statins, it's not enough to show that this CETP inhibitor, dalcetrapib or torcetrapib, can show improvement. It actually has to be better on top of what is already known. So you don't have to beat placebo; you have to beat standard of care. And unfortunately, drugs like dalcetrapib just didn't beat standard of care, and the molecule was abandoned. What's interesting is that I've just come across some new data that was published in 2020 that shows that use of dalcetrapib can actually reduce the risk of type 2 diabetes against placebo. So maybe and that doesn't surprise me that the drug itself would do something, just not something on top of, in addition to the LDL molecules. So, and before I forget, there's a bunch of show notes that capture a lot of this stuff if you're interested. But this was a really compelling story because you had an area of huge unmet need. There was this, uh, obesity epidemic, and a lot of money went into these drugs, and there were a lot of them. And slowly but surely, they all were abandoned. And all these drugs, anacetrapib, dalcetrapib, evacetrapib, they didn't have mortality signals the way that torcetrapib did, but for whatever reason, they just weren't enough in terms of their clinical punch to do enough on top of standard of care that the whole platform was abandoned. And the story, the HDL story, is essentially lost to history because they just sort of walked away from it. But I draw lessons from this particular element. One of them is the farce of treating a number. So the first sort of a head scratcher on this is that you're trying to increase HDL, which is a molecule on a blood panel. It's not an actual like functioning outcome. It's associated with cardiovascular positive part of cardiovascular outcomes, but just increasing the number itself may not necessarily do the job. And I liken this to my neutrophil to lymphocyte ratio story about how Tisabri can drop your NLR ratio. And I think that has positive effects clinically, but in essence, it's just a number. And if one wanted to play devil's advocate, you could cite this HDL story and be like, well, we increased HDL and it didn't do anything, or at least didn't do anything significant. So that's something that happens in medicine where a physician or whoever, a healthcare provider, will be looking at your labs and be like, oh, this number is lower than it needs to be, or lower than I want it to be. Let's give you something that will change it. And this is a textbook example of how just changing a number didn't lead to anything positive. But the other thing that I draw from this is the fact that it may not be HDL's fault. It could have just been the way that you went about it. So it may be that HDL has a good functionality, and a lot was learned about HDL in this whole process, which oftentimes happens with drugs, as you discover things you didn't know once you start experimenting with the system. But it just meant that these CETP inhibitors failed. And that maybe have been the most straightforward way of getting the effect on HDL that you wanted. But it really highlighted that inhibition of this enzyme is actually, or this transfer protein is actually what doesn't work. Levels of HDL still have value. You just, the system was more complicated than you had thought. And so the reason why I think that this is important is that Alzheimer's has gone through a similar story where amyloid beta, which is this single monomer molecule that aggregates in your brain and forms plaques, is thought to be sort of a central hypothesis on what causes Alzheimer's. And a lot of amyloid beta antibodies have been investigated to figure out if that we can do something by removing these monomers, and a lot of them have failed. And so people were sort of skeptical that the amyloid beta hypothesis was valid because all these drugs failed. But then the approach has gotten so much more nuanced where it's not just targeting amyloid beta, but it's targeting specific subspecies of amyloid beta. And that's still on relatively thin ice in terms of its functionality. Um, so these therapeutic hypotheses are nuanced. They're not. It's not quite as simple as we would like it to be. Nature rarely ever is, especially if you want to change it. But what's interesting is that the difference between Alzheimer's and this cardiovascular space that I've been referring to is that there isn't anything else. So aducanumab gets to go up against placebo. It has an opportunity, if it gets approved, which I think it will, to be a toehold. So it's not like the future of Alzheimer's, but I mean it is the future of Alzheimer's. But in the future, we will look back on aducanumab and think like, oh man, we were so adorable with that first step. Because ideally we'll build a whole assortment, an armamentarium on top of aducanumab as a platform, because pharma will have the motivation because there has been some way of drawing commercial success for a product, because there's no research if there's no dollars. And unfortunately for torcetrapib, statins were already there. And so, it wasn't enough, or at least dalcetrapib, I should say. So it wasn't enough to just beat placebo. You had to beat standard of care. So with atherosclerosis, we had a standard of care, and we don't have one for Alzheimer's. So that's, I think, is an important difference between the two. But anyway, I thought this was a fun story. I may do some more of these dead drug episodes. I can think of several, and they're really, I think it's worth bringing up the past, because it is one of the reasons why pharma companies charge so much money for their drugs. They have to kind of recoup the losses, these high-profile losses, and close to $800 million was invested in torcetrapib. But anyway, if you're interested in more good drugs, feel free to subscribe to my channel.